Good afternoon. Welcome back. So today we're going to continue the discussion on linear models by focusing on two of the earliest neural network models. Um, but before we get started, I wanted to see if there were any questions from last time. All right. Well, these two models, the perceptron and Adeline, as I mentioned, are among the two oldest artificial neural networks. They're certainly the oldest that we will be studying. The first one, I think I mentioned last time, due to Frank Rosenblatt, was the result of him attempting to model the retina in the eye. And at the time, there was a belief that recognition, I think pattern recognition, basically took place in the eye, that there wasn't a whole lot that happened back in the brain for just simple classification and simple recognition tasks. And so his hypothesis was that he could build a model of the retina to do basic classification. And the interesting thing is that, limitations aside, he succeeded. The second model, the Adeline network, I think I also mentioned last time, Adeline is sort of an acronym. It can be broken down as either adaptive linear network or adaptive linear neuron. This was due to work by Woodrow and Hoff. I believe the date for that work was around 1960, so it was a few years later than the work from Rosenblatt. But much of what we are going to see going forward in terms of looking at more complex and more recent neural nets, in large measure, can be attributed back to this early work, which is why we're going to spend a good bit of time on these two models. So we're going to begin with the perceptron. And much of what you're going to see will look pretty familiar. So this is a two-layer neural network. Where this is our input layer, and this is the output layer. Although if you actually go back and look at Rosenblatt's original paper, he would have taken that input layer and laid it out as a grid. Again, trying to, in many ways, capture the spatial view of the retina. When we look at this output, we calculate a function phi of y, which is defined to be the signum function applied to this weighted sum that by now we're getting rather familiar with, where the signum, or SGN function, or sometimes simply called the sine function, but not to be confused with the trigonometric sign, is either +1 or -1 for x greater than 0, x less than or equal to 0. So as you can see, it's a step function. Sometimes also called the Heaviside function, or a hard limiter. And these are all going to be terms that I'll probably use somewhat interchangeably. I think I tend to use hard limiter the most when talking about neural nets. And as you'll see, that SGN or sign function, hard limiter function, has some pretty significant limitations, and we'll be looking at ways to relax those limitations later. All right, so with this, we can proceed to define what we're doing with the perceptron. So we're going to let W be a vector of weights. See if I can be a little bit more consistent here. It's a vector of weights. And X be a vector of inputs. So these are weights. And these are inputs. All right. And we will be, for the notation that I'm going to be using to describe this model, I'm actually going to be drawing on Rosenblatt's original notation, which you're going to see is a little bit archaic, but it's also kind of interesting to talk about it the way he talked about it. And then what we'll be doing is we will be calculating a z equal to that SGN function applied to the inner product of the weights and the inputs. And for our purposes, we are going to go ahead and assume that theta is equal to 0. And by doing that, we're not going to directly include it in the model. We will include it in the model later, but for the purposes of what Rosenblatt was doing, we're not. Okay. Some more notation. Our classification space will either be positive or negative. So we're dealing with a two-class problem again. And we'll see a little bit later how we can relax that. And we'll define F to be our concept space where F can be divided into a positive space and a negative space. So being the concept space, this is basically the examples, the set of possible examples that can be fed into the perceptron. So all right. I've now run out of space that I need on the whiteboard, so this is a good time to pause to see if there are any questions so far. Okay, so what I'm going to do next is actually give you the training algorithm for training a perceptron.
New page.
All right. So the first thing we do is we choose an initial weight vector at random. One of the things that's rather interesting is the intercept of f positive and f negative 0. What do you mean by intercept? We were taking the union of two sets. Are you asking if the intersection is empty? Yes, they're disjoint, so the intersections are empty. Okay, so anyway, we're choosing an initial weight vector W at random. And then what I'm going to do, I'm just going to describe what you do with a single example. Recognize that you're going to loop through your training data. So we're going to choose some example X from the set F, again, at random. All right. Now, if X is a positive example, and Z, and you'll recall that we said that Z is equal to the signum of the inner product, and Z is less than or equal to 0. So right off the bat, when we're looking at this, this should look a little bit familiar because it's a very similar type of a thing that we did with the Winnow algorithm, where we're looking at an example of a misclassification. The example is positive, but the network is currently returning a negative classification. And you remember that in that case, what we did was we promoted. Well, we're going to do something kind of similar here. We're going to take the weight vector and we're going to add the example to it. If, on the other hand, X is negative and Z is greater than or equal to 0, and if you want to, get rid of the equality on one of them, that's fine, because if you're doing this in order, if equality hits on the first one, it's not going to hit on the second one because you're going to skip out. Although I didn't write it that way, but again, very similar to what we saw in Winnow, where in this particular case, we would want to demote. Here, we subtract the example from the vector, from the weight vector. Else, do nothing, because the network got it right. Okay, so at the moment on the surface, this looks very similar to Winnow, but we don't have that alpha term that we're dealing with. So we're not multiplying or dividing by alpha. We are using the example directly to modify the weights. Any questions about, that's the whole algorithm. And then, like I say, you loop through the data. You would loop multiple times until convergence. So this is not a single pass algorithm. But I want to see now if there are any questions about the algorithm. Okay, so I'm going to give you a theorem. It's a relatively long theorem, and we're going to see how things go today and tomorrow, because again, I want to make sure that I've covered everything you need for the quiz. And if there is time remaining tomorrow, I may come back and prove this theorem. But if not, it's no big deal. But I do want to make sure that you get the gist of what we're proving here. All right, so, and by the way, this particular theorem was not proven by Rosenblatt. It was proven by Marvin Minsky and Seymour Papert at MIT in 1968-69. You can find it in their famous book called Perceptrons. And we'll talk about that book here in a second. The theorem goes like this. Let F be a set of unit length vectors Oy. All right, and I'm going to pause for a second because on the surface, this might seem to be a limiting factor, except you can take any vector and you can normalize it just by dividing by the length of the vector. So in fact, this does not limit the power of the perceptron by itself in any way. What it does is it makes the math for proving the theorem much more convenient. And let W be an initial weight vector which again, we were generating randomly. If there exists a unit vector W prime and a number delta greater than 0, such that W prime transpose X is greater than delta for all, here, I'm going to abbreviate that. X in F then the perceptron learning algorithm will update W only a finite number of times to find such a W prime. And that's the theorem. Now, what the heck does it mean? So this particular theorem is sometimes simply called the perceptron convergence theorem. What it basically is saying that under the conditions that are laid out in the theorem, where we're dealing with unit vectors, and we are able to find whatever this delta is. And by the way, this condition right here combined with this is extremely important, because taken together, what that means is there exists some weight vector W that will correctly separate the positive and the negative subsets of F. Now, it doesn't look like it says that in the wording of the theorem, but in reality, it does, because of the way that we are handling that inner product and that threshold delta. Okay, so remember that this is a linear model. So those two things combined basically are saying that the concept class is linearly separable. All right, this is a good time to pause and talk about that perceptron book for a minute. When Minsky and Papert wrote that book in the late 1960s, one of the key results in that book was the fact, well, two things. There are two key results. First, that perceptrons could only learn linearly separable classes. Up until that point, nobody knew that. In fact, the perceptron had done so well on what are frankly toy problems, they thought that it was much more expressive in terms of what it could learn than it really was. And so Minsky and Papert kind of threw the brakes on, saying, hold on, it's not really that powerful. The second thing they did is they actually showed what was necessary to modify the perceptron so that it would become powerful enough. And that's where we will later in the course start talking into multi-layer and eventually deep neural networks. But the challenge at the time, back in the 60s, was nobody knew how to train them. And so this was a major blow to neural net research. And all of the funding pretty much dried up as a result of that book. And contributed to what was becoming known as the AI winter at the time, which was much more pervasive than just neural net research. But the point being, working in neural nets was considered a career killer after that book came out. And it wasn't until the mid-'80s that there was a resurgence in neural net research, because they figured out how to actually train these multi-layer networks. Now, as we'll see when we get to that conversation, there were actually some earlier results that also solved the problem. They just didn't know at the time that that's what they had done. But we'll talk about that later. All right, so we have linear separability as a key precondition for this to converge. Why is that the case? Because if you think about the error function associated with this particular problem, what we find is that that function is actually convex. And so this search algorithm is basically searching this convex function to find a minimum error position, and when it does, it stops. And the theorem is saying you only need a finite number of steps, a finite number of modifications to that weight vector to hit that minimum. All right. Again, if we have time on Friday, I'll prove this theorem. I have a feeling we won't have time, but let me pause for a second to see if there are any questions. All right, well, what we're going to do now is we're going to talk about the Adeline network.
New page.
On the surface, the Adeline network is going to look almost identical to the perceptron. But there are a couple subtle differences. We still have a weight vector. And we have our input vectors. So no change there. And we are going to be calculating this weighted sum, just like we did with the perceptron. Although the first change here is that we're not going to assume that the threshold is 0. And you recall, again, going back to Winnow, you had to tune that threshold. Well, as it turns out, you don't need to. We can actually learn that threshold. So to do that, we're going to let W0 equal theta, which now changes this to be and if you like adding instead of subtracting, no big deal. In the process of learning, we will learn the correct sign of that weight. So that's all fine. And so it's simply becoming a new input to our network. But what we're going to do is we're going to clamp the input for that particular node to 1. And then when we're done, after we're done training these weights, W0 will be the threshold. All right. So the learning rule is, in fact, a little bit different. So to do this, let's let O be the output of the network. And we'll let D be the desired or the target output. In other words, this is, from the supervised learning perspective, the ground truth value that we're trying to learn for a given example. And so from here, O is going to be a function of the weights of our input, and D we can denote with a function T to represent target. And we're going to calculate that error that I mentioned with the perceptron convergence theorem. And what we will use here, and by the way, just looking ahead, this is what Woodrow and Hoff used, but later we will change this function as well. For now, we're simply going to use squared error. Okay? And the reason that is significant is because you can imagine an extra box stuck on the output of the network where this is O. But our target, or D, is coming here. At least that's what we would normally compare with, except by passing it through that step function or the hard limiter, we're snapping it to plus or minus 1 or 0 to 1, depending on which one you use. but we are calculating the mean squared error relative to the raw output of the network. And when we do that, our weight update looks like this. All right, what's eta? So this thing here, eta is a number between 0 and 1, and we call it a learning rate. Or you could think of it as a step size that basically scales how large of a jump you make in correcting the weight as you train. All right, so a couple key differences. From the perceptron, that is. We calculate the error before the step function, and we update on all examples whether right or wrong. And that's the Adeline algorithm. So I think, again, this is another good chance to see if there are any questions. What we're going to do next, however, is dig a little bit deeper to figure out what's exactly going on with these two algorithms. But anyway, let's see if there are any questions first. All right.
New page.
So let's take a closer look at what these algorithms are doing. And to do that, we're going to talk about a fairly common method for doing optimization. So a method for optimizing some function f of x. That method, and some of you may have already guessed what's going on, it's called gradient descent. Now, by calling a gradient descent, that is suggesting we're minimizing the function, which is probably true. If you want to maximize the function, then we often call it gradient ascent. But the principles are the same. So what we're going to do is we're going to look at these training algorithms from the perspective of doing gradient descent. All right, so you'll notice that for both algorithms, we sort of had this general form where we were taking a weight vector and we were going to modify it with or without a learning rate. I mean, in the perceptron case, eta was equal to 1. In the Adeline case, you would usually set it something less than 1, times some change to the weight. And you'll notice that, again, in Adeline, that delta W corresponded to the target minus the actual times the input. And for the perceptron, that delta W consisted of the input itself. So both algorithms follow this form. And what we want to know is what's going on with that delta W, because that's really the heart of both learning algorithms. So I mentioned that both through the perceptron convergence theorem, we were focusing on optimizing error. And I mentioned that with Adeline, we were evaluating performance of the Adeline network based on squared error. So there's something about error here. So when we look at that function, whatever it happens to be, it turns out that what we are doing from a gradient descent perspective is calculating the gradient of that error with respect to the weights. And for those of you who have not had Calc 3, basically that gradient is a vector that consists of the individual derivatives of the error with respect to each of the individual weights. And the way you take a partial derivative, I mean, if we've got d variables here, one for each weight, then for each of those partial derivatives, you're taking the derivative with respect to the given weight while assuming that all of the other weights are held constant, which then just reduces it down to a single variable derivative. All right. So what that means is that we're saying that our update rule, by doing gradient descent, is calculating the gradient and using that as the actual update. So this is rather interesting. How are we doing on time? It's getting close. I do want to talk about that, but we'll come back. So let's go back and take a closer look at the error function. And we're going to do this from the perspective of Adeline. Now for Adeline, you can think of that error as actually being a function of the weights. Now, to be completely correct, I should put both variables in there, the weights and the inputs x, but for convenience, we'll leave it this way. And we can calculate an average or mean squared error as this. And I probably, let's see, how hard is that? I'm going to change that to be consistent. We'll use the D notation to indicate that that's our desired output. All right, so this is our error. It's calculating the mean squared error over the entire data set D. To calculate the gradient of the error with respect to the weights, what we find is that this basically reduces to this. And that should look kind of familiar, because that, if you just look at the part inside the sum, you'll notice that that is exactly what we used for the update rule for the Adeline network. So Adeline was doing gradient descent. And what this does is it also highlights kind of two different strategies for training. And we've talked about this before as well. Actually, I'm going to talk about three strategies. The first strategy is what we call batch updating. And that's what this gradient expression is doing, because effectively what it does is it takes all of the data and runs it through the network and calculates the gradient for each example, but does not make any updates until the end, where it then takes all of those corrections and averages those corrections and then applies that average to the weight vector. The second strategy is called incremental updating. And the only difference between incremental and batch is that you update the weights immediately after each individual example. Now, a third method, which has become quite popular, especially in the deep learning community, involves what are called mini batches. And this falls in between the batch updating and the incremental updating, where what we do is we randomly select a subset, usually a small subset of the training data, and use that to do a batch update. And then you go back and you get a new random sample and do a batch update, and so on. The other thing that's interesting about this, if you take 2 and 3 together, especially if for the incremental approach you are selecting the example at random, we get what is commonly known as stochastic gradient descent. Virtually all modern implementations of neural net training methods employ some form of stochastic gradient descent. Are there any questions? Why would you choose batch over incremental? That is a very good question. So one of the issues that you run into, in fact, I'm glad you asked it the way you did. The incremental approach, you can argue, should learn faster because you are doing more frequent updates. However, it's not as stable as the batch updating, because by doing averages over these updates, you've basically smoothed the update process. So batch updating is slower, but it's more stable. You get fewer oscillations, and you tend to get to a local optimum more directly. Now, the thing that is interesting is, and it's why I'm glad you asked the question the way you did, because you did not ask about the mini batches. The advantage to the mini batches and why they have dominated is that you get the best of both worlds. By working with smaller batches, it's faster to do the updates. You have more updates going on. It's not as many as single example updates, but you still have somewhat of an averaging effect, which tends to stabilize the learning. So it's a nice compromise between the two methods. Does that answer your question? Okay, great. Any other questions? All right, we have 5 minutes left. I have one other thing I would like to talk about because Friday is going to be busy. I want to go back to the perceptron algorithm for a minute.
New page.
Because the question is whether or not we can say anything about the perceptron algorithm doing any kind of gradient descent. All right. So for this, we will assume incremental updates because that's what the perceptron algorithm does. And we're going to start by looking at it from the Adeline perspective, but we'll restrict targets to +1 and -1. And we will also assume, do I have to assume that? Yeah, I have to assume that. And assume that we are applying the step function before updating. Before updating. Which now makes it non-Adeline, but this is actually what the perceptron does. And you remember that, I'm not going to define that yet. Yeah, you remember that what we did, if we had a positive example, and let's suppose that I actually get it right. And what we're going to do is we're going to apply the weight update from Adeline with this one modification, where our weight looks like this. Now, if it's a positive example, the target is +1. And we're subtracting that vector product, which was +1 times, do I have the, times the input. If you do the math, you'll notice that the right-hand term cancels out. And so you actually get no change, which is exactly what the perceptron update rule said. If it's correct, don't change it. And you'll find that exactly the same thing happens if it's correct on a negative example. And again, -1 + 1 is 0, so that right-hand term cancels out. But what do we do when it's wrong? Now, for this one, we have to contrive it a little bit. So we're going to let eta equal just 1/2 or 0.5. So for this one, it should be positive. But we get negative. So for this, again, applying the gradient descent rule, and notice here we changed it from a +1 to a -1 because it was incorrect. And when we do that, lo and behold, this becomes the perceptron update rule of just adding the example. And we get the same kind of thing if it should be negative. where we end up subtracting the example. And so what this has done is it shows that the perceptron learning is gradient descent. Even though on the surface it didn't look like it. All right, we're out of time, but we can pause to see if there are any last minute questions. All right, well, thank you, everybody, and we will see you on Friday.